Hello everybody, welcome to my presentation. My name is Askin. Today I will talk about my master thesis. It is called as a hand and eye tracking system for hands-free control of a robotic exoscope. Before I start my presentation, I want to talk about myself a little bit. I graduated from University of Çankaya in 2011 from Computer Engineering Department. Then I started my master in University of Hacettepe, Department of Computer Animation and Game Technologies. I continue my study in University of Tübingen. I completed my master thesis there. I have experience on full cycle development on health, military, and automotive area for 5 years. Currently, I am working MHP, a Porsche company, and Porsche Digital Lab as a software consultant. Microsurgeries are powerful techniques that enables us to save many lives with a little to no discomfort. What microsurgery is a general term of surgery requiring microscope, and using an exoscope for microsurgeries is another option. The exoscope is a telescope-based solution which is attached to high-definition camera to provide a magnified view on screen in front of the surgeon. A medical assistant can freely position the whole device close to operating field from any desired direction. Using head and eye tracking, we provide a rotation command to the robot arm for automating position of camera view. We combine augmented reality and robotics and present a new solution to microsurgery. And we provide a live 3D magnified view to the user's natural field of view through a head-mounted display. We use as hardware a head-mounted display from HTC Vive and an eye tracker. It's from Puppy Labs, and also we used a robotic arm, Kinoa JCO2, and also 2 webcams from Logitech Pro 9000. In our early studies, we also used PS3 webcam instead of Logitech Pro, but it was not really compatible with Windows. So we switched to Logitech and it was efficient. Unity was used to render 3D video feed into users' VR system. OpenVR is used to control VR set. Also, Pupil SDK is used to track user pupil motion for camera, and ROSE is used for robotic arm call. It's fed with data collecting from VR, headset, and SDK. We used a webcam texture class in Unity 3D to provide live video stream from 2 cameras, and 1 texture per each eyes was created so that one eye could only see 1 layer via the curling mask method in camera class. As such, we provided 3D vision to the user via the HTC Vive display. The HTC Vive comes with a built-in inertial measurement unit consisting of 3D axis gyroscope and 3D axis accelerometer. And with this IMU, the user's head rotation was estimated with an accuracy of 1/10 of a degree. Moreover, to estimate the gaze position, we mounted a Pupil Lab eye tracker to the HTC Vive. The most common way to represent rotations in 3D space is by 3x3 matrices, quaternions, and Euler angles. We decompose head rotations into roll, pitch, and yaw angles. The roll like angle around z-axis while tilting the head in the frontal coronal plane, and pitch is angle around y-axis, and yaw is angle around x-axis. These 3 angles were estimated within the SteamVR and then transferred to an open source middleware robotic operating system via the WebSockets. On the ROSE Rose machine, and these values were published on a Rose topic message passing methods. Similarly, using People Labs gaze SD card for Unity, we sent the gaze position from the eye tracker to the Rose machine. In order to test the performance of our system, we asked 12 untrained participants to perform an object manipulation task similar to common surgical simulation studies. And they were from 3 females and 9 male, average age like 28. And we used a board with 3 nails where 2 nuts were placed over the one of the nails. And participants were asked to move the nuts from one nail to another using tweezers. For the experimental task, a board having 3 nails was used, as you see on the screen, and 2 nuts were placed over one of the nail, and the user were responsible to do 3 same tasks with different system, and the task was to remove the nuts from a nail to another nail. In the first task, the user had to move nails without using any headset or controller, and second task was to remove nails, and third with headset, HTC Vive headset, as you see on the video, and third was by using HTC Vive controller. And second and third task was not always with the same order for the user, in order to remove learning effect on the starting always with the same tool. Now she's switching the other task, so every time she needs to move her hand from the board, and as you see, she loses a lot of time just because of that. When nuts rolling out of the screen, I was removing back to the screen. There was an initial position, it is between 2 nails, and then user started it from that position. Now he is trying the same experiment with a handheld controller again. I am also holding a joystick here. It is to start and stop robot, just another useful way to do it. Because sometimes I needed to use for an emergency position, for example, an extreme movement of the user because of the rotation of the robot. If you move extremely, it's directly coming out to user's face. Here another user trying to do experiment. Most of our users they are students, research assistants, and PhD candidate. Some of them has experience on VR environment, some of them are not. And As you see here, he made an extreme movement to the right, and now he had some difficulties to reach experiment area to use teaser, just because it is not in front of him anymore. And another participant, and he started to experiment from baseline, just trying all tasks using any tool, and now he started with glasses again. And first with only headset and the other with handheld controller. And another happy user complete all tasks without having any problem in short time. Here I stopped the robot, and then he just tested the glasses. This table shows the task completion time for each participant. The data from 2 participants who had motion sickness problem were omitted for this analysis. On average, participant finished the baseline condition, condition A, in 39 seconds, and the handheld controller condition B is within 209 seconds, and the hands-free condition C with automatic reposition system is in 100 to 80 seconds. Typically, participants had less error when a nut falls out to the board when performing the hands-free condition compared to handheld controller condition. The questionnaire was graded by the users to compare head and eye tracking system to hand console from 1 to 7. And this figure shows the answers of the questionnaires by participants. When we look at the result of the comparison of both systems, we see that rotating the camera-mounted robot by head-mounted display is easier than handling by the controller. And the highest average is for question 14, when we ask about if the various functions in these well integrated. And when we look at the answers of the questions 2, 4, 5, 6, and 10, we can see that the users easily learned how to orientate head-mounted display. When we ask about integration of whole system, in last 3 questions, we can claim that the system was not found complex by the participants. We also used a NASA task load index to show the users characterize our system within a relatively high mental load that requires extra effort. And for our untrained participants, the major difficulty was to see the platform from an unnatural angle with a high magnification view. However, this is a common practice in microsurgery. Our users often pointed out that weight of the head-mounted display which needs to be reduced in the future systems. In summary, we tried to demonstrate the potential of hands-free robotic exoscope for camera viewpoint automation, and we aimed to show that the manual interaction with an exoscope, even a robotic system, creates delays during an operation. On average, the task completion time was 208 minutes for our hands-free solution. However, with handheld controller, it took on average 329 minutes for participants to finish the task, and we concluded that it is more efficient to use a hands-free solution instead of handheld controllers. Thanks for giving me this opportunity to present my master thesis to you. Have a nice day.